So I'm taking a radioactive decay problem. So I write here time. And the next column here is n of t. So for the time being, let's say it is 100 at 0 time. So for the time being, let's define a value lambda. I take, okay, 0.03. So we can see the decay of this nuclide and we can compute it. We can compute the amount of nuclides, the number of nuclides that will be present after some time. So I take a step of 2 and I can compute it is equal to n naught, which is 100. Okay, for simplicity I write 100 times e raised to the power minus lambda. So let's pick the value of lambda I $2. Okay. The value has been selected times the value of t. So this is fine, 94.176. And let's keep repeating this calculation for future times. And this can be accomplished by dragging the formula downwards. So a few more calculations. Well, time requires calculation to be done by selecting 2 cells. Okay, that will be fine. Now let's compute the probabilities. Now at this stage, I can compute the decayed nuclides or the nuclide that have been converted to daughter nuclide. Decayed nuclides or the daughter nuclides. So at the beginning, there were no daughter nuclides. Now at this stage, the daughter nuclides are 100 minus this value, right? So about 6 nuclides decayed in the first 2 time steps, right? I can repeat that thing. The number of nuclides decayed in this interval. So from 94 to 88. So this is the number. Similarly, the number can be computed by subtracting the successive values in the parent nuclide, right? Between 2 successive steps. Now probability. Probability of finding decayed nuclides. Decayed nuclides. The nuclide decays divided by original present, right? Original present at that time. So that is the probability definition. And also we have taken the time step of 2. So probability should take into account the time value. In this calculation, it is also evident that about 6 nuclides have life about 2 time units, 2 minutes, okay, for the time being, if we consider lambda is per minute. Then the next 6 nuclides, they have the lifetime of 4 minutes. These nuclides, they were in parent state up to 6 minutes and so on. So all nuclides have different lives. And now let's do the probability calculation. So this logically will begin from here. And I write here the number of nuclides decayed. These many nuclides decayed out of total. At this time, the present amount of nuclides were this one, right? 100. And also the time step, let's normalize it with the time. So that is 2 in our case. But if you like to generalize it, then we can write this value, end of time step minus the beginning of time step. That's more uh, elaborate. So 0.029. Probability of decay. Counting number of nuclides divided by the total number of nuclides present at the time step, at the beginning of the experiment, and also divided by the time step, length of time step. And my claim, behold, this number is going to remain constant. Therefore, it is a decay constant. Here we go. Here we go. Decay constant 0.029. When rounded to two digits, it is 0.03. And that is the value I started with. I started with the numerical value and then I computed the same value from the probability concept. So that is the decay probability.